Okay, so we have a warm up here. So, I'm going to ask the sub to give you a few minutes. So, sub, if you could pause this for a second, that would be great. Otherwise, I'm going to go ahead and go for it. Oh, let's move this guy. There, now we'll be able to see it better. Okay, okay, so I'm editing this video and I don't want to open up the whole slideshow again. So I just wanted to give you some notes before you started taking it. So I want my sub to be prepared to start and stop this as needed. And also, it's totally fine with me if the kids use their phones or other devices to watch this video on their own and take their notes. But kids, as a warning to you, if you're using your own phones to watch a video, you better be watching the video. If the sub sees you doing something else, the sub can take your phone. Okay? Good. Please be good for my sub too. So we have a dodecahedron, so that is a 12-sided die, and it's got the numbers 1 through 12, which we've already discussed. And we want to know the probability of each event. So rolling a number less than 9. Okay, so remember a dodecahedron would have the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, so which ones are, how many are less than 9? So that does not include 9. So there's 1, 2, 3, 4, 5, 6, 7, 8. So 8 are less than 9. And there's 12 possibilities. So that's an 8 out of 12. Or if I reduce that, 4 goes into both of those. So that would be 2/3 or a 67% chance. 66.7 or 67%. So a multiple of 3. Well, remember, a multiple of 3 is a number that goes into 3 evenly, or that 3 goes into evenly. So multiples of 3, so this is part B, are 3, 6, 9, and 12. So there's 4 of them. And there's 12 choices, so that would be 1/3. A number greater than 6, so numbers greater than 6 would be 7, 8, 9, 10, 11, and 12. And that is 1, 2, 3, 4, 5, 6 of them. 1, 2, 3, 4, 5, 6, yep. So that's 6 out of 12, or a half. And not rolling a 10, there would be 11 numbers that aren't 10, so that would be an 11 out of 12. Okay, good job. Okay, so I'm going to ask that the sub give you about 10 minutes. You can talk to your partners, and you have to make a list of your 2 favorite ice cream flavors and your 4 favorite ice cream toppings. And so you're allowed 1 ice cream flavor and 1 topping. You have to make a list of how many different combinations. So for instance, let's say I like banana and strawberry ice cream, and then I like walnuts, pecans, caramel, and whipped cream. So I could have a banana with caramel, or banana with whipped cream, or and so on and so on. Okay, so you guys go ahead and make a choice, and then in a few minutes we'll discuss it. Okay, so How many choices did you guys get? Well, you should have come up with 8 choices, and we're going to talk about why you should have gotten 8 choices in a little bit. But really, you should have had 8 different combinations. So you should have had 8 different Okay, next. So we have this interactive tree diagram, and we're going to go ahead and go to that. So we have to do a little bit of maneuvering so you can see how it works. But this is just a way that we can use to I don't know what that means, but I'll say okay. Okay, teacher. I guess I'm not logged in. So let me log in. Okay, let me just pause for a second while I'm trying to figure out how to log in. I'd be happy to pause, but I can't see what's happening over there. Let's try it again. Let's try it this way. Go this way. Okay, so here we are. I'm finding it. I think we're going to be good. I want the red accelerated, and I want chapter 10, probability and statistics, and then 10 floors, compound events, and the interactive tree diagram. Alright, so let's choose a problem. Let's do the pizza shop. Okay, so for a pizza shop, we have 2 choices for the crust. We can have a thin crust or a stuffed crust. So I'm going to bring that in here, and the stuffed crust here. Then I have styles. So I could have Hawaiian. So I could have thin crust Hawaiian, thin crust Mexican, thin crust pepperoni, or thin crust veggie. And for stuffed crust, I could have Hawaiian, it's Hawaiian, Mexican, pepperoni, or veggie. So this is these tree diagrams are a nice way to organize our possibilities. Okay, so let's try another one. Let's try, I don't know, maybe, I don't know, what's this, MP3 players. Okay, so I could get a 4 gig, an 8 gig, or a 16 gig. and then in different colors. So this would be the different combinations. So I could have silver, blue, pink, black, black. I could have an 8 gig with the same color combinations. And I could do the same thing with a 16 gig. And then I get my choices. Let's see what else they've got. A meal. Oh, this has 3, so this is kind of cool. So for an appetizer, I could either have nachos, soup, a spinach dip, and then for my entree choices, I could have spaghetti or fish, and then spaghetti or fish, spaghetti or fish. And then for my dessert, I can either have cake or ice cream. So I can have nachos, spaghetti, and cake. Nachos, spaghetti, and ice cream. If I could get the ice cream to show up, that is. There we go. Or I could have nachos, fish, and ice cream. And nachos, fish, and cake. And then I could have soup and spaghetti and cake, and soup and spaghetti and ice cream. Anyway, you see all the different possibilities. Okay, so they do have these little so these are just tools that we would use to make we would make tree diagrams to organize our possibilities. So there are tools that we're going to use. Okay, so I'm going to pause and go back to the screen. Okay, so we're back. So we went over this. So again, here is one of the filled out tree diagrams. So again, we're going to use these to organize our sample spaces. Okay, next. So now we're going to talk about what dependent and independent events are. And our learning target 12.2 is I can calculate the number of possible outcomes of 2 or more events. And then I guess we should add that we could find their probabilities also. So first of all, we have what is called the fundamental counting principle. And we did discuss this some last class. So I want you to write this down. The fundamental counting principle, we have m possible outcomes for event m, and then we have event n, which has n possible outcomes. So the total number of outcomes of event m followed by event n is m times n. Okay, so let's just look at the, let me go back a slide or 2. Let's look at the pizza crust. There were 4 styles and 2 crusts. So for instance, we had the 4 styles, 2 crusts, and 4 styles. So we had 2 choices for crust. I want to multiply that by the 4 styles, so we should have 8 possible outcomes or styles. So let's go back and make sure that we got 8. So if you notice this, here we go. We have 1, 2, 3, 4, 5, 6, 7, 8. So we do. We have 8 choices. So that's how the fundamental counting principle works. So it's the number of possibilities or outcomes for event M times the number of outcomes or possibilities for event N. So n little n times little n, in this case 2 times 4. Okay, so let's look at this. How many different outfits can you make from the t-shirt, jeans, and shoes in the closet? So, you know, if you count, I know all the answers are already written down here, but if you count, here the pants are in the top on the shelf in the closet, and it looks like there's 4 pairs of pants or jeans. Oh, goodness. Okay, yeah, so right here we have 4 pairs of pants or jeans, and then we have 1, 2, 3, 4, 5, 6, looks like 7 t-shirts, and then 3 pairs of shoes. Okay, so it looks like we'd have the 7 times t-shirt, 7 t-shirts times the 4 pairs of jeans and the 3 shoes, and 7 times 4 times 3 is 84. So we have 84 different outfits. Okay, so let's look at this one. This lock has 3 wheels. Each wheel is numbered from 0 to 9. So 0 to 9 is actually how many numbers? So you might think 0 to 9 is 9 numbers, but it's actually 10. It's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there's 3 wheels. So in the first wheel, there's 10 choices. And in the second wheel, there's 10 choices. Oh, no, that's not the question, I'm sorry. In the first wheel, so wheel 1, wheel, let's try this a different way. Actually, we might edit this. Okay. Try this again. Okay, so we have the wheel. We have wheel 1, 2, and 3. So there's 10, 10, and 10. Okay. So the least 3-digit combination possible, what they're saying is what they'd add up to, and it would be 0, 0, 0, 0, right? So it would be 0 plus 0 plus 0, which is 0. And the greatest 3-digit combination possible would be 999, which is 27. And then how many possible combinations are there? That'd be 10 times 10 times 10, which is 1,000. And then this is the same part B, this is kind of worded funny. There are 10 possible outcomes for the first, 10 for the second, and 10 for the third. So it'd be 10 times 10 times 10, or 1,000 again. Alright. Now this lock is numbered 0 to 39. So 0 to 39 is, remember, actually 40 numbers. 0 to 39 is 40 numbers. It's 1 through 39 and then 0. So 40 numbers. and you know, you go right, then left, then right again. So how many possible combinations are there? So for the first spin, so there's spin 1, spin 2, and spin 3. So for spin 1, there's 40, and spin 2, there's 40, and spin 3, there's 40. So it'd be 40 times 40 times 40, or if you like, 40 to the third. And that is 64,000. So 64,000. Okay, now in part D, we have 4 wheels. So right away you're thinking, okay, maybe this one's harder to break than the other one, right? So this one, this 64,000, is way harder to break than this 3-code lock here, because there was only 10 choices for each one. This has 40. Now this has 4. So 0 to 9 is actually how many choices? So wheel 1 would have 10 choices, because 0 to 9, remember, is 10 choices. Wheel 2, A through J, well, we have to count those. So we have to count A through J. So A, B, C, D, E, F, G, H, I, J. So that's 10 choices. And then K through T for wheel 3, so H, I, J, K, L, M, N, O, P, Q, R, S, T. So that's another 10. And then 0 to 9 is 10. So this would be 10 to the 4th. Or 10 times 10 times 10 times 10. So it would be 100 times 100, or 10,000. Okay, so which lock is more difficult to guess a combination? So clearly, this old-fashioned lock right here is the harder one to bust. Okay? Alright, so we're going to find the number of total possible outcomes for these. Okay, so we have size and we have flavor. So here we have size choices. Size. There's 3. And flavors. It looks like 1, 2, 3, 4, 5, 6, 7. Looks like 7 flavors. So the total number of outcomes would be 21, 3 times 7. Okay, and then the next one. Okay, so you try this one. Again, you know, hopefully this will stop a second. You try on your own. If not, you can just watch it. Okay, so we have appetizers. I'm going to write apps. And then we have the entree and desserts. So there's 3, 4, 5 appetizers, right? 1, 2, 3, 4, 5, yep. And for the entrees, we have chicken, beef, spaghetti, or fish, so that's 4. And then we have 3 desserts, cake, cookies, and ice cream. So that's 5 times 4, which is 20, times 3, which is 60. So there would be 60 outcomes. Alright. So what's the deal here? What's the problem with this? So we have a true-false quiz, and it has 5 questions, so there's an error here. Well, that's right. For a true-false question, there's 2 choices, true or false. So there's 2, and all of these have 2 choices. That's good. And there are, let's make sure, 1, 2, 3, 4, 5 questions. So that's right. They have the right amount of 2s. What's the problem? Right, we're supposed to times these. These should be times 2, not plus 2. Okay. So these are times and not plus. So this should actually be 2 times 2 times 2 times 2 times 2, or 2 to the 5th, which is 32. Alright, good. Now we're going to fill out this exploration. Okay, so I'm going to make this a little easier by calling these. So first of all, there's 3 marbles in the bag, and there's 2 green marbles and 1 purple, and they're in the bag. And we're going to randomly draw a marble, and then we're going to put it back. So the marble we took is going to go back in the bag. And then we're going to redraw a second time. Okay, so for the first draw, we're going to call this one green 1, and this is green 2, and this is purple, right? So the first one, we could draw green 1 and then put it back, or draw green 2 and put it back, or draw purple and put it back, right? So for the second draw, let's say we did draw green 1, we put it back in. So green 1 is available again for us to draw, and green 2 is still available for us to draw, and our purple is available. Okay, and then here we have green 2 with green 1. Oh. So green 2, and then I could get green 1 again, green 2, or purple, and then green 1, green 2, or purple. So anyway, I'd have here like a green green, a green green. Oh my goodness, for Pete's sake. So green green, green green, or green purple, and green green, green green again, or green purple. And this would be purple green, purple green, or purple purple. So the question is, does the probability of getting a green marble on the second draw depend on the color of the first marble? So what do you think? Okay, it doesn't. Since I put the marble back, I still have 2 green marbles in there, right? So if I drew a green marble out, then I'd put it back in, and I'd still have 2 green marbles and 3 marbles total. If I pulled the purple the first time, I'd put it back, so I'd still have 2 greens, 1 purple, and 3 marbles total. So this does not depend. So this is a dependent event. And how many possible outcomes would there be? Well, we had draw 1 and draw 2. So there are 3 choices for draw 1 and 3 choices for draw 2. So we had a possibility of 9 outcomes. And if you look down here, we have these 9 outcomes right here. Green, 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 purple, green, 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 purple, purple, green, purple, green, purple, purple. So 9. Purple. People eater. Okay. Alright. So in activity 2, this time it doesn't make it clear, but this time we're not replacing the marble. So this time it says right here, without replacement, right here. That's the only place it says. So we're going to draw the marble out, and once we draw it, it's going to stay out. So this is still green 1 and green 2, and then the purple marble. Okay, so here, this is where it changes. Let's say I draw green 1. So green 1 is now out. So all that's left is green 2 and the purple purple marble. It's a tongue twister. Okay, now let's say on the first draw, I drew the green 2 marble. So that means I have green 1 left and the purple marble left. Okay, let's say on the first draw I drew a purple, so that means I have green 1 and green 2 left. So this would be green, green, green on the first draw, green on the second draw. Then I would draw green, purple. This would be green, green, and green, purple. This would be purple, green 1 and purple, green 2, but still purple, green, right? So let's talk about the choices. For the first draw, and second draw. So there were 3 choices the first time, right? But then one of those marbles stays out. So that means the second time there would only be 2 choices. So it'd be 6. So my sample space would be 6. 1, 2, 3, 4, 5, 6. Okay? So in this case, does the probability of getting a green marble on the second draw depend on the color of the first marble? And it does. So this is what we would call a dependent event. Oh, I did make a mistake here. I am so sorry. You're probably all screaming at me. It did not matter, so this is an independent event. Sorry about that. That's independent. That's an independent event. Okay, so an independent event is when one event will not change the probability of another. And that would be just the probability of A times the probability of B. Now the probability of a dependent event where one changes the other, that means if we're not replacing, it'd be the probability of A times the probability of B after A. So in our case of the marbles, after we take out one marble, we're going to have less marbles left, and the probability of getting them will also change. So let's look at a couple. Okay, so number 5, we're going to spin the spinner and flip a coin. So I think for this one, goodness gracious. Okay. For this one, I think it's best if we go ahead and draw the table just this first time. Okay, so we're spinning a spinner. And there's 4 choices, 1, 2, 3, or 4. And then we're going to flip a coin. So after we flip a coin, we're going to get heads or tails. So we could spin a 1 and then get heads, or spin a 1 and get tails. You could spin a 2 and get heads, and spin a 2 and get tails. And the same thing for 3 and 4. Head, tail, head, tail. So our sample space, if we're keeping track here, for the spinner, there's 4 choices, and for the coin, there's 2 choices, so 4 times 2 is 8. So we should have 8 outcomes here, and if you look right here, we have 8. 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 choices. So the probability of spinning 3 and flipping heads, let me switch colors up here. Spinning 3 and heads. So there's 2 ways of looking at it. There's the actual just figuring it out, and so theoretically, and then there's looking at the tree diagram that we do. So first let's go with the just figuring it out scenario, because that's always going to be the fastest. You don't want to always have to draw the tree diagram, but if you get stuck, you can always draw it. So to spin a 3, how many 3s are there on the spinner? There's 1, so that would be 1 time, and then how many choices are there? There's 4 numbers, 1, 2, 3, and 4. And then we're going to multiply it by the flipping heads. So heads, there's only 1 head, and there's 2 choices, heads or tails. Okay, now let's check. Do you think that this is an independent or a dependent event? Does, when you spin something and then flip the coin, does the spinner affect what happens with the coin? Clearly they don't. One does not affect the other, so these would be what we call independent events. So we would just multiply these. So that would be 1/8. Okay, and then to check that, what we said is we spin to 3. So here's the 3, and we flipped a head. Okay, so that means there's only one where there's a 3 and a head. So 1 out of these 1, 2, 3, 4, 5, 6, 7, 8 choices. So 1 out of 8. So that's how you could do it using the tree diagram. But again, that's not necessarily, you don't need to actually do this. Draw the tree diagram. Okay, so spinning an even number and flipping tails. So spinning an even and flipping tails. So there's 2 even numbers. There's the 2 and the 4. And there's 4 choices. And then a tail is still 1/2. So this would be 2/8. And 2/8 can be reduced to, right over here, 1/2. Okay, spinning a number greater than 1. So how many numbers are greater than 1? Well, 3 of them, 2, 3, and 4 are greater than 1. And there's still 4 choices. And the tail is still 1/2. So that'd be 3/8. And then not spinning a 2. So that we'll do here. Not a 2. So not a 2 means a 1, 3, or 4. So there's 3 choices there. And heads is still 1/2. So that's 3/8. Okay, and again, you can use a table to check those out. So like spinning a number greater than 1 means a 2, a 3, or a 4, and flipping tails. So right here we have a 2 with the tail. Right here we have a 3 with the tail and a 4 with the tail, so that's 3 out of the 8 choices. Okay, so if you get stuck, draw your tree diagrams. Okay, so this one's a little harder. We're not going to actually draw the tree diagram out for this, but let's talk about whether this is an independent or a dependent event first of all. So randomly we're going to choose a tile. So how many tiles are there? 1, 2, 3, 4, 5, 6, 7. So there are 7 tiles. So let's just make some notes for ourselves up here. So we have 7 tiles. Okay? Now, after I choose one of the tiles, I'm not going to replace it. So that tile is gone from the table, right? That's in our tray if this was like a Scrabble game or something, or Rummikub. The tile would be gone, right? So there's only 7. Once we take that out, then there's only going to be 6 tiles left, right? Okay, so for the first draw, there's always going to be 7 tiles. The second draw, there'll only be 6 tiles, right? Okay, so our sample space will be 7 times 6, which is 42. Okay, so find the probability of each compound event. So the first one, number 9, is choosing a 5 and then choosing a 6. Okay, so a 5 and then a 6. I think I'm going to change my color too. The red shows up a little better. Okay. So a 5 and then a 6. So how many tiles with a 5 on there are there? Okay, there's 1. And in the first draw, there's 7 tiles. So the probability of drawing a 5 is 1 out of 7. Now the probability of drawing a 6, now this has changed. That 5 is now out of my pile of tiles. So there's only 6 tiles left. And how many 5s are there? 1. So this would be 1 times 1, which is 1, and 7 times 6, which is 42. So it'd be 1/42. Okay, number 10, choosing an odd number and then a 20. Okay, so our odd numbers, let's make some little notes for ourselves here. Our odds are 5, not 6, 7, not 8, 9, and not 10 or 20. So there's 3 odds. And the first time I draw it, I'm going to write it over here. There would still be 7 choices, right? Now there's only 6 choices left the second time, so it's going to be out of 6. Now a 20. Okay, so choosing a number, or so now a 20. Now is 20 an odd? No, 20 is an even, so that means I couldn't have already drawn the 20 because I drew an odd the first time. So when I draw the 20, I have 120 left, and then there's 6 choices. So this would be 3 over 42, and that can be reduced to 1/14. Okay, choosing a number less than 7. So which numbers are less than 7? Okay, let's put these numbers in order. That might help things out. We have a 5, 6, 7, 8, 9, a 10, and a 20. So numbers less than 7 would be just 5 and 6, right? 5 and 6 are less than 7. And there are 2 possible choices, and there are, again, 7 tiles. Now this is hard to read, but this says a multiple of 4. So which of these numbers are multiples of 4? Well, 8 and 20 are multiples of 4. So that would be 2, and there's only 6 tiles left. So this would be 4 out of 42, which can be reduced to 2 out of 21. And then choosing 2 evens. Okay, so 2 evens. Well, on the first go around, how many even numbers are there? Well, the even numbers are 6 8, 10, and 20. And there are 4 of them, and there are 7 choices. Okay. Now, I already used an even number, so when I go back in to draw again, now there's only 3 choices left, because I already used an even number, so there's only 3 evens left, and now instead of having 7 tiles, I would have 6 tiles, so this would be 12 over 42, and 12 out of 42 reduces to 2 sevenths. They're both divisible by 6, right? So 2 sevenths. All right, pretty easy. Okay, error analysis. So what's the problem here? So we have to describe and correct the error in finding the probability. So we randomly choose one of the marbles. So there's 4 marbles, all different colors, green, blue, red, yellow. Okay. So we choose one of the marbles. We don't replace it, so we don't replace. Then we're going to choose a second marble. So what is the probability of choosing a red, then a green? So probability of red and green. Okay, well, looking at this, there's 1 red marble, the first to go around, and there's 4 marbles to draw from. But remember, I'm going to not replace it, so that makes this an independent event, which means that our sample space is going to change. Now I've taken the red marble out, so how many marbles are left to choose from? 3, and how many of them are green? 1. So this would be 1/12. Okay, then we have these problems to do. And I think we're almost done. So we roll a number cube twice, and we're going to find the probability of each event. So when we roll a number cube, so a dice, when we roll a dice twice, does the first outcome change the second? No, it doesn't. So this is an independent event. So let's write that down. This is independent event. Okay, so rolling a 3 twice. Well, when you roll a die, how many choices are there? Well, there's 6, 1 through 6, and there's only 1 3, so it'd be 1 times 6. And then when I roll it the second time, nothing's changed. It's still 1 times 6, so 1/36. Okay, rolling an even number and a 5. So an even and a 5. So the even numbers are 2, 4, and 6, and there's 3 of them, and so there's 6 numbers to roll. And a 5, there's only 1 of them, and there's 6 numbers to roll. So this would be 3 times 1, which is 3, and 6 times 6, which is 36. So 3/36, which is 1/12. Good. I was just looking at my answers and I thought I had a different answer. I did not. It was right. 1/12. Okay, rolling an odd and then either a 2 or a 4. So an odd, there's 3 odds, 1, 3, and 5, and there's 6 total. And then rolling a 2 or 4, there's 1, 2, and 1, 4, so there's 2 good outcomes out of 6 possible outcomes. So that'd be 6/36, which is 1/6. Okay, number 4, rolling a number less than 6 and a 3 or a 1. So a number less than 6. And then a 3 or a 1. So less than 6 would be 5 choices. 1, 2, 3, 4, or 5. So 5 numbers are less than 6. out of 6 possible. And then a 3 or a 1, there's 1 1 and 1 3, so there's 2 good choices out of 6. So this would be 10 out of 36, which can be reduced by 2, so that would be 5/18. And that is the correct answer, 5/18. Okay, so let's look at this. We have a magician and a magic hat and some letters in the hat. So you may choose a letter from a hat randomly, A through J. Now without replacing, okay, so this without replacing is super important. That means that this is a dependent event. Okay, and then I think that to do this, it's best if we write the letters down. So they're A through J. So A, B, C, D, E, F, G, H, I, J. So it looks like there's 10 letters. So the probability of choosing an H and then a D. So how many H's are there in the hat? There's 1. And again, there's 10 choices. Okay, now that H came out, so the H is no longer in the hat. So now, how many choices are there? 9. And there's 1 D. That was an accident. Anyway, there's 1 D. So 1 times 1 is 1, and 9 times 10 is 90. So you have a 1 in 90 shot at drawing an H and then a D. Okay, choosing a consonant and then an E or an I. So choosing a consonant, and then an E or an I. Okay, so remember consonants are not vowels. So the not vowels here are B, C, D, F, G, H, and J. And there's 1, 2, 3, 4, 5, 6, 7. There are 7 consonants and there's 10 letters. Okay, so you have a 70% chance of drawing a consonant first. Okay, and then we have to draw an E or an I. So an E or an I, there are 2 E's and, or sorry, 1 E and 1 I, so 2 good choices. And we know that the E or the I hasn't been pulled out because an E and an I are, E and I's are vowels, not consonants, so it hasn't already been pulled out. So 2, theoretically it hasn't been pulled out. And now there's only 9 letters to choose from, so this would be 14 out of 90. And 14 out of 90 is 7/45. Okay, choosing a vowel. So vowels are A, E, I, O, and U. So in this case, A, E, and I. So there's 3 vowels and 10 choices. Then we have to choose an F. Well, we know that the F hasn't been chosen, so there's only, so all the consonants are we know an F hasn't been chosen because it's a consonant. So that means there's only 1 F, and there's only 9 tiles, or 9 letters, sorry. So this is 3 over 90, which would be 1 over 30. Okay, and number 8, choosing a vowel and then a consonant. So a vowel and then a consonant. So remember there were 3 vowels and we have 10 choices, and then a consonant, there were 7 consonants, but we're only going to have 9 choices. So that'd be 21 out of 90. Okay. Number 9, you have 3 clasp bracelets, 4 watches, and 5 stretch bracelets in a jewelry box. So how many pieces of jewelry are in my jewelry box? Well, 3 plus 4 is 7, plus 5 is 12. So it looks like I have 12 pieces of jewelry in my box. Okay, and I'm randomly choosing 2. And I'm not replacing them. I'm choosing 2, and I'm going to wear both of them. So I'm choosing 2. So this would be an independent event, or sorry, a dependent event. Dependent. Okay. And what's the probability that we're going to choose 2 watches? Okay, well, the first go around, there's 4 watches to choose from and 12 pieces of jewelry. Now, I kept one of the watches. I pulled the watch out. That watch is no longer left to choose from. So now I have 3 watches left to choose from and 11 pieces of jewelry. That says 11. So this would be 4 times 3, which is 12. And 12 times 11, which is 132. So that's 12 out of 132, and when I reduce that, I'm going to get 111. So the probability of drawing 2 watches out of my jewelry box would be 1 out of 11. Okay, and the last one. A bag contains 3 marbles. Does the tree diagram show the outcomes for an independent or dependent events? So let's talk about it. The bag has how many marbles? 3. Okay. Now, the first draw, there's 3 choices. There's green, red, and blue. Okay, so that's good. There's 3 choices the first time. Now, if I put the marble back, that would make it an independent event, and I'd have 3 choices here. But I don't. I have only 2 choices each go around on the second draw. So that means I'm not putting the marble back. That means there's only 2 marbles left to draw in, right? So this is a dependent event because I'm not replacing. And I know I'm not replacing because I have the marbles left. Okay, and I think that's the end of it. It is. Okay, so I hope you were good for the sub. You can watch this at your leisure or in class. I'm going to leave notes either way. Okay. Done.